Before I jump in and take questions on the assignments, though, I want to address. There's one last little piece of section 2.2 that would show up on the second assignment that we haven't really talked about yet, enough at least. I want to take a second and just address that. So,
I don't get the second time at all.
second part at all. Okay, yeah. So we need to go through a few things there. So derivatives. Derivatives are essentially rates of change. That's really what they are, right? We can think of them in really in two ways, but derivatives and rates of change are synonymous. A lot of times we think about a derivative graphically, we think about it as a slope, and that's perfectly fine. That's what it is. Graphically, it's a slope. But even if we think of it as a slope, what is a slope? A slope is just a rate of change of a function, right? So we can take something very mathematical, like if we're graphing, let's say, we've got some function, f of x, and if we calculate the derivative of the function at, let's just call that point C, so the slope of this line would just equal f prime of C. What does that mean? Isn't that really just the rate of change of the function? Okay, can I get everybody to turn around, please? This is really, I mean, you gotta get this fixed. Okay. So isn't that really just the rate of change of the function with respect to x? Right? Now think what we're doing. When we calculate a derivative, so f prime of x as just being f of x plus delta x minus f of x over, it's the limit of all this stuff, right? Over delta x, as delta x goes to 0. We'll just focus on that difference quotient. What is that? It's just asking us how much is the y value of the function changing for a certain change in the x value. That's what a rate of change means. A rate of change always just compares the way that two quantities change. And so we're about to take the really exciting step here of jumping from strictly mathematical stuff into stuff that's not strictly mathematical, right? So we could take very soon, and we could even talk about it a little bit today. Well, actually, today's a good day to start talking about it. We could talk about a physical quantity. Like, let's just say, hypothetically, that we've got some spherical balloon that's filled with air, okay? And let's say what's the formula for the volume of a sphere as a function of r? What's the volume of a sphere? Pi r squared is the area of a circle. Okay, it's something, but it's a pi r cubed, but there's a constant out front. 4/3, yeah. So there's the volume of a sphere in terms of its radius, right? So as we pump air into this balloon, the volume is going to change and the radius is going to change, right? Now what we're going to do here in the not too distant future is we're going to be able to look at something like that and say, okay, if air is being added at a certain rate, if the volume is changing at a rate of, let's just say it's, I don't know, 100 cubic centimeters per second, we'll be able to answer the question, when the radius of that balloon is exactly 20 centimeters, how fast is the radius changing? Okay, something like that. Now that's jumping ahead a little bit. For now, let's take a simpler question. Let's just ask the question, how fast does the volume of a balloon change with respect to a change in its radius, with respect to its radius, right? This is an interesting question. It may not sound interesting, but it is interesting if you look at it here. How would we do that? We're going to find the derivative, aren't we? Now, we're used to talking about things like f of x and x, right? But isn't this just the very same thing, only the names have been changed a little bit? Instead of an f, it's a v. Instead of an x, it's an r, right? So we've still just got a function, our dependent variable, of some other variable or independent variable r in this case. So the dependent variable is a function of the independent variable, right? Instead of f and x or y and x maybe, it's v and r. So if we want to differentiate this, we now have the tools to do this, right? We could calculate v prime of r, and what's the answer going to be? Okay, so yeah, so what are we going to do here? What's the variable that's being acted on when we differentiate? R, right? The other stuff is just a constant, right? 4/3 pi is just some number. That's just a constant, right? So really, this is just another example of differentiating a constant times a power function, right? What was our trick for differentiating a power function? Okay, good. We dropped the exponent out in front. We're going to multiply by the exponent and then drop the exponent by 1, right? So aren't we going to get 4/3 pi times 3, which is what? 4 pi r squared, right? Okay, that's interesting. That is interesting in a bunch of ways if you think about this. Math, it just gets so interesting when you get the tools to investigate it more precisely. Question?
Yeah, that seems more like 2.1, but with 2.2 you're using sine and cosine. So how are we supposed to transfer that such back and forth between the sines?
Okay, we'll look at one of those too. I would guess people maybe have some troubles with these kind too, is that right? Oh, good. Good. Okay, so while we're on the subject here, though, I want you to take a look at this. There's something really interesting going on here. So if we look at this function, right? If we look at the rate of change of volume as a function of radius, look what it's doing. That's a parabola, isn't it? Right? It's a parabola that's going through the origin, and then this 4 pi is just making it taller, right? It's just stretching it out vertically.
Yep.
If I multiply, remember what we do if we have something like y equals ax squared. X squared is just our parent regular parabola, and if a is a big number, we're going to stretch it out vertically. If it's a number whose absolute value is less than 1, we're going to squash it, right? So I'm not going to get the scale right here, but would you agree that this just looks like that? Mathematically, it would be symmetrical about the v-axis, but can you have a negative radius? No, okay, so we just discard the other half of the function because it's non-physical, right? We're talking about geometric, or it's non-geometrical at least. So here's what it looks like. This is r, that's v. What happens? What happens there? As the radius increases, what happens to the volume? It increases, but it increases not proportionally, right? Yeah, so if we double the radius, we're going to do a lot more than just double the volume, aren't we? Okay, does that make sense? So that's interesting, right, that we get that kind of relationship. There's something else going on here that's really interesting. 4 pi r squared might look familiar to you. What is that?
Isn't that
Go ahead.
sine and cosine?
No. Something else going on.
Tangent.
No. Something about 4 pi r squared. Remember, we're talking about spheres.
It's like 4 times the area.
Okay, it's 4 times the area of a circle, which is like, if we took a cross section through the sphere, right through the center, right? Then the area of that cross section would be pi r squared. So it's kind of interesting that it's 4 times bigger than that, but that just opens up even another phenomenal similarity here. There's something else though that we're missing. What is 4 pi r squared is important? That's the surface area of a sphere. How about that? Weird, isn't that?
Spherical.
So now think about this. This is really cool. The rate of change of the volume of a sphere with respect to radius is equal to the surface area of the. That's amazing. I mean, it's if you really think about it, if you sat down and thought about that, which I'd encourage you to do for about a half an hour, you might get to a point where you'd say, okay, now that really does make sense in a way. You can draw some, you can see it's kind of a causal relationship, but that's interesting, right? Okay, so sounds like we're okay with that, right? If we're trying to explore rates of change, all we're doing is we're just differentiating to find what the rate of change function is, right? Make sense? Okay. Sounds like the questions are coming from the sine, cosine stuff. Is that right?
Yeah.
Is that, Delaney, is that where you
Yeah,
have? Okay. So how about if why don't I pull up the assignment and we'll look at a
Yes.
couple of those.
I could figure out the first one, but after that it was kind of new.
Okay. Yeah, you bet. Oh, hang on, that's the wrong one.
It's so cool. I would like a laugh.
We'll see. I don't know, maybe. If we've got time. Okay, this stuff. So give me which one do you want to look at? Give me a couple we'll look at here.
Let's do this one.
Okay. All right, let's do this one.
Yeah, the first one. It's
Oops.
What are you guys doing?
Okay, we ready? Yeah, I don't like this. I don't like that our time is so constrained here, and then every time I'm ready to go, I have to kind of reel people in. That's got to be your responsibility. You know what's going to happen in college if you do that? I just want to prep you. You're going to get your butt kicked out of class, and you may or may not be invited back. So just be prepared for that, and it'll be embarrassing, and it's, you probably won't do it, but shouldn't do it now either then. Okay, so this guy, we're supposed to differentiate. Does this notation make sense? If they're saying, if we want to calculate dy dx, we're going to take the derivative of y when y equals this function negative 15x plus 8 cosine x, right? Another way of saying that is, we're just going to take the derivative with respect to x of that function, right? Does that make sense how they've, good, okay, because that's important, that the notation makes sense. All right, so we're just going to differentiate this. How? Let's talk about our approach to this. And this is really important that we're able to kind of model the correct thinking on this. How do we tackle a problem like this if we're differentiating something with two terms, first of all? We separate them, yeah. And the wording we use, and I think this is also good to kind of get this, be able to talk with this language. We're going to differentiate term by term, right? So it's like we're going to walk across the room step by step, one step at a time. Well, we're going to differentiate this one term at a time, which makes it much, much easier, right? So we're going to get back then, what for the derivative of the first term? Negative 15, right? Good. And there's a bunch of ways we could look at that, but really it's just negative 15 times the derivative of x, right? The derivative of x is just 1. Agreed? Okay. What about the second one? Okay, good. So what we've really got here, we've got this 8 out front. We can just leave the 8 out front, right? Because when we're differentiating a constant times a function, we just leave the constant alone and differentiate the function. Now, what's the derivative of cosine x? Negative sine x. And that's just going to be something you're going to have to remember. We're going to end up with about, I don't know, probably something like a dozen standard forms of derivatives that you're just going to have to just remember. But you'll remember them. By using them, you'll just remember them automatically. Yeah, it is. The derivative of cosine is negative sine x. So then what's our final answer?
Negative 15 minus 8 sine.
That's it. Exactly. That's it.
Oh,
Okay? No biggie. That's it.
Oh, I like this stuff. Okay, so would that make sine inside, would that be negative cosine?
No. When you differentiate sine, you don't get a negative. It's just positive cosine. I'll drop this one on you now, even though I wasn't planning on doing this till later. We're going to add derivatives to all the 6 trig functions, right? All the regular, the sine, tangent, secant, and then the co-functions, cosine, cotangent, cosecant. Here's a little trick to remember this. Whenever you're differentiating a co-function, you always get back a negative answer. But if you're differentiating a regular, non-co one, they're positive.
What does co mean?
Well, I mean like cosine,
Oh,
cotangent,
okay.
cosecant. Yeah. Okay, so moving on. Another one. Give me another, throw another one at me from there. Just keep going, okay.
And velocity and stuff, that.
Okay, we can, so this one they're asking us, you probably can't read that. They're telling us a body's moving in simple harmonic motion with position function, S equals F of T. So here's the position function, S. And they just want us to find the velocity at, well, maybe we'll look at this one. Yeah. It's not a really hard one, but it's some good physics here too. There's gonna be some harder ones, and I'm sure I'll look at least one hard one too. Okay, so there's the position function. And really, you know, this is just a minor thing, but probably we should write that as S of T, right? Because position is a function of time, equals that. There's the position function. Okay, physics types, and now even non-physics types in here. How is velocity related to position?
So this is the derivative.
No, velocity is the derivative of position, right? Okay. So we would say then that V of t equals S prime of t, right? Now, think what that means. Really a much better definition for velocity that we haven't talked about in physics yet because we're not doing calculus in there. But the best definition of velocity is the rate of change of position, right? With respect to time. But we can always just assume it's with respect to time unless we tell the difference, right? Does that make sense? So velocity measures the rate of change of position, okay? Which, yeah, we can think of as the slope of a position time, or, you know, position time graph. Sure, we can do that, but what it really is the rate of change of position. Okay, so to get the velocity function here, all we have to do is just differentiate that, right? So what are we going to get when we differentiate? What's the first term give us? Zero, right? Derivative of a constant is always zero. Second term?
Positive.
Okay, well, so yeah, you're right. We're going to get a negative 9 times the derivative of cosine t, which is,
Negative sign.
Positive.
so our final answer then is just going to be, good, positive 9 sine t. Good. That's not what they're asking though, is it?
No.
What they're really asking here is they want to know, yeah, this is v of t, but they want to know what's the velocity of the body at t equals pi over 6, okay? Seconds.
So
pi
that's
over
a
6.
33.
So they're asking then, what is v of pi over 6, which is just 9 times sine pi over 6. What's the sine of pi over 6?
1 half.
1 half.
Oh,
So we just get back 9 halves meters per second, right?
Wait. Okay.
Okay? So I mean, you're putting a lot of stuff together at the same time. But this relationship now, we're gonna get a lot of practice here in the near future at taking derivatives. Think what you're doing. You're starting with some function and you are deriving a new function related to it, right? We know how it's related now. It's the rate of change of the original function.
okay.
You're gonna get to use your ever increasing bag of tools to be able to quickly, without having to do limits and all that nonsense, go straight from the original function to the derivative just by differentiating, right? We're gonna add a whole list of derivative tricks that allow us to get there in a quick, efficient way. We've got just a couple of that. We've got a couple trig derivatives, sine and cosine, and we've got the power function derivative, power rule. That's really about it. Okay? If we look at one harder one, is there a harder one?
This one has like 3 parts.
Oh, this one has like 3 parts to it?
It's
Oh, okay, velocity, speed, and acceleration. Oh, gotcha. Oh, yeah, that's good. Let's keep going.
I think it's velocity.
Okay, so, oops. Okay, so they want to know velocity, speed, and acceleration. Okay, now, we do need to do a little physics tutorial in here for people that aren't in physics. What's the difference between speed and velocity?
Speed is distance over time and velocity is change.
Okay, good. So speed is, now, velocity is a vector quantity, right? Which means it can be positive or negative, right? So, does that make sense? So real quick, if I'm walking on a line up here, I'm just gonna have very simple motion, and that's the positive direction. When I'm moving in this direction, my velocity is positive because my velocity is taking me in the positive direction, right? If I'm walking in this direction, my velocity is negative because I'm going, the arrow that points in the direction I'm moving is in the negative direction. Vectors always have two parts. They have a direction and a magnitude and a number, right? So if I'm walking at 2 meters per second in this direction, my velocity is positive 2 meters per second. In this direction, it's negative 2 meters per second. What's my speed the whole time? 2 meters per second. What speed is just the number part of velocity. That's really it. Just the magnitude of velocity. But it's always positive, right? So yeah, so you can think of it as being the absolute value, sure. Okay? So then in this case, what's the speed? 9 halves, yeah. Same as the velocity because it was positive. What if the velocity had been negative 9 halves? It would have been 9 halves. It gets a little more complicated when the velocity is, in multi-dimensions, and then the velocity is expressed a lot of times as a component in the x direction, a component in the y direction, and a component in the z direction. And then you have to do some other stuff, but it's essentially boils down to the same idea we just discussed. Okay, what about acceleration? We got to get acceleration now. How is acceleration related to velocity?
Changing velocity.
Yeah, good. So acceleration is the rate of change of velocity. So somebody describe for me then, how is acceleration related to position? Of the, okay, it's the rate of change of the rate of change of position. See what I'm saying? Right? That's kind of, you got to think about that for a second. It's the rate of change of the rate of change of position, because the rate of change of position is the velocity, right? Now we'll come back and revisit that real quickly. But for now, we're just going to relate acceleration to velocity. So A of t is just v prime of t. Well, if that's v prime of t right there, what's a of t? What's the derivative of that?
Oh.
9 times
Zero.
derivative of sine t is cosine t. So it's going to be 9 cosine t. Okay, now you might notice something sort of interesting about this. There's a relationship, and this is always true with simple harmonic motion. With simple harmonic motion, the acceleration is related to the displacement in an interesting way, right? Notice that I don't want to get too far gone on this, but think about what is simple harmonic motion. Simple harmonic motion would be something like, for example, let's say that we've got out in space, we've got a mass fixed to a spring and say that spring is attached to something very, very massive, so it's not going to move. So here's the big object over here. Here's the spring. And there's the massive object. If I stretch this thing out and let it go, what's it going to do?
Spring.
Yeah, the technical term is it's just going to boing back and forth. Yeah, that's the word we know. So if I stretch it out here and let it go, let's say I let it go from here. At some moment in time, isn't the relative to, let's say, like its rest position right there? So this is going to be a little bit of a positive displacement, right? If I pull it this way and I let it go, at this point right here, where the position is still positive, it's still stretched a little bit beyond it, like where it would be if I didn't boing it, right? Which direction is the acceleration going to be acting in? Yeah, isn't the spring pulling it that way?
Yeah.
Yeah, you see that? So look at that. Now when it gets compressed over here,
Then it goes forward.
yeah, then the position is negative, but now the acceleration is positive. So notice, isn't that kind of cool that you can see that mathematically? Because look at the sign right there. Compared to right there, it's positive. Yeah, right? Make sense? Okay, so then if we want to just finish this question,
I thought we did.
Well, we didn't answer the very last part, which is what is the acceleration at t equals pi 6. So a of pi 6 would just be what? Yeah, cosine of pi 6 is square root of 3 over 2. So I'd get square root of 3 over 2 times 9. So I just get that. 9 radical 3 over 2.
What's your final answer?
That's it. That's it. That's the acceleration. Okay. Make sense?
Got it.
Okay. Sure. Okay, oh, it is a good one. Yeah, so write the volume of a cube. Well, this, you can't see that very well, I bet, can you?
That's a lot already.
Yeah. What if I do this?
Delete
Oh,
the
that's better.
question.
Can you guys see that now? Is that big enough? Okay. So write the volume V of a cube as a function of side length S. Okay, so what is the volume of a cube as a function of side length S? That's cute. Sure. Okay, so part A is just going to be V of S equals S cubed. Okay, now we want to find the instantaneous rate of change of the volume with respect to S. Well, what is that? That's V prime, right? That's just V prime of S. Now, there's two ways we could write this, and I want you to see that they really mean the same thing. So we could write it as dV ds, which looks like a slope, but you can also think about that as a change in volume over change in side length, right? So it really is just a rate of change, isn't it? How fast is the volume changing as the side length changes? Or we've been calling it that. Either way, it's fine. So V prime of S then is what? 3s squared. Yeah. Okay. We want to know what is the rate of change of the volume. So V prime at S equals 1 and S equals 5. So this one right here, if we're evaluating at S equals 1, that's really just V prime of 1. And what's the answer? 3. Right? Right here, this is really just V prime of 5. So what's that? Yeah, 3 times 25 would just be 75. Okay? Make sense?
Yeah.
Okay? All right. I think you're good. Yep. Okay.
Are you gonna be in the lab tomorrow?
Yeah, I think. Is that, you tell me, is that necessary to have one more day? Okay, that's fine, I'll do it. 54, I mean, it's probably not worth going down there now. You do? Okay, well, let's go then.
No, wait, was it 6 minutes?
6 minutes?
It takes 3 minutes to pack it.
I'll go through another one, how's that?
Yeah.
Yeah, exactly, by the time we get logged in, that's gonna be pretty, we're gonna be pretty tight there. That's- So what are we looking at?
How about one quick problem?
One what?
Quick problem.
Okay.
Interesting.
Okay, what about this one? Let me make this bigger. Let's just talk about a couple of these. We don't have to necessarily do the whole thing. Okay, so what about this? Now, if they give us the position function, right? And they want us to find acceleration. Okay.
Each time the body is 0.
Yeah, each time the velocity, find the body's acceleration each time the velocity is 0. Okay. So we got a couple things to do there. I'm going to let you do this, but let's talk about it a little bit. So first of all, I would have to, if I want to, I need to find the velocity function and the acceleration function, right? How do I find velocity? Differentiate that, okay? What kind of function am I going to get if I differentiate that one?
Pretty quadratic.
What's it going to be? It's going to be quadratic, isn't it? Because we can see that the powers are going to drop by 1, right? So it's going to go from cubic to quadratic. In general, how many solutions does a quadratic have?
2.
Okay, 2. Maybe, I mean, up to 2, right? It doesn't have to have, it might have 0 real solutions. It might have a double real solution, so there's only 1, or it might have 2, right? Okay, so to find the times when the velocity is 0, what would we do with that velocity function?
You would put 0
Not for t,
for y.
for v, right?
Put it in for V of T.
Does that make sense? Because we're now I don't want to do too much this. I really want you to do this, but we'll just talk about it kind of conceptually. So if I differentiate, would you agree I'm going to get v equals something, right? If I want to ask the math gods, or I don't know if this is kind of math or physics gods, maybe both. They hang out a lot anyway. So if I ask the math/physics gods, when the velocity is equal to 0, what I'm really doing is I'm just setting v equal to 0 and solving the equation, right?
Are you solving for t then?
So we're solving for t. Now doesn't that make sense?
Yeah.
We're going to set v equal to 0, and we're asking the question, when does that happen? Well, now we've got a quadratic equation in terms of t, right? So by solving for t, I'm really answering the question, when? When is v equal to 0, right?
Yeah.
So that allows me to find the 2 times. Now the other part of the question, though, what they're really asking for is the acceleration at each of those 2 times. So what do I have to do to find acceleration?
Put them into you like
Now, hang on, think back, think. How's acceleration related to velocity? It's a derivative. Right, so I got to go back to my velocity function and differentiate again to get acceleration, right? Then you're going to plug those numbers in, right?
wait.
Right?
Okay.
Because you want to know, we're going to get a of t equals the derivative of velocity. Alexis, what kind of function is a of t going to be? Shh. Listen. You told me v was a quadratic.
Oh,
So if I differentiate again, what's that going to be?
linear.
Yeah, it's going to be linear, isn't it? Right? So the acceleration would be a linear function, and we're just going to evaluate that linear function at each of the 2 values of t, right?
Sure thing.
You'll get it. You got it. So okay, so I will give you a lab day tomorrow, and then Wednesday we're gonna push on a little bit. Okay? Yep. Sure I can. Oh, I gotta take a roll real quick though.